there. Hello and welcome everyone to the first webinar for 2022 for the Australasian Radiation Protection Society. I'd like to open by acknowledging the traditional and cultural custodians of the lands upon which we are participating from today and pay respect to elders past, present and emerging. I also want to quickly mention that there is another ARPS webinar event happening next week on the 5th of April. That particular one is titled Dose Estimation for Medical Incidents and Accidents, and the presenter is Zoe Brady, Chief Physicist from Diagnostic Imaging and Radiation Safety Officer at the Alfred Hospital in Melbourne. So hopefully everyone can tune into that. I think it's like this presentation in terms that it is probably of great interest to a lot of people who are also non-ARPS members. So please get in touch with your colleagues that you think might be interested in that presentation also. So today's presentation is live electromagnetic energy testing from Telstra's 5G mmWave smart apartment. It's quite an exciting one because it's a dynamic presentation. We'll get to see a bit of action shots and moving around an apartment, see some of the findings from the experiments from measuring EM fields in the smart apartment, and a bit of an insight into how this technology will improve or influence the standard of living. So it's brought to us today by three presenters. We've got Mike Wood and Steve Isker of Telstra and Phillip Knipe of Total Radiation Solutions. So I'll give you a quick background. Mike is a distinguished professional with Telstra and a principal of Telstra's Electromagnetic Energy Strategy, Governance and Risk Management Program. Mike graduated from RMIT and has over 30 years experience in mobile network deployment, EME and community consultation, and leads Telstra's 5G EME program. Steve received his Bachelor of Honours degree in Electrical Engineering from the University of Melbourne and a PhD from RMIT in 2012. Since joining Telstra in '82, he's worked in the fields of EMC and EMF safety and has published in peer-reviewed journals in these fields as well. And Phillip Knipe received a Bachelor of Science degree in Physics in 1990 and a Masters of Philosophy in Physics in 2002 and has a PhD in Physics as well from Murdoch University. In 2002, Phillip set up Total Radiation Solutions, which holds ISO accreditations for 17025 and 17020, and has published in peer-reviewed journals on electromagnetic fields. So that's the brief versions of the bios. I didn't want to embarrass everyone or draw it out too long. A quick little bit of housekeeping. So questions are most welcome. I will ask that they are submitted by the chat function, so we will keep the microphones muted throughout for the participants. And then at the end, there'll be a question and answer session where I'll put those questions to the presenters. So without further delay, I'll hand over to you, Mike and Phil.
Fantastic. Well, look, welcome everybody. It's great to be here. We're live on mmWave as we speak. We're live in the 5G smart apartment. We're going to give you a bit of a look around before we've got a couple of slides to set the scene about what we're doing. Just behind us, you can see there are two spectrum analyzers. The one on my left is actually measuring the mid-band or the 2600 and 3600 5G mid-band, if you're familiar with those mid-band frequencies. We're going to show you that in the chart afterwards. The one on my right, and whether your eyesight is that good, you can actually see some activity there. That's 800 megahertz worth of 5G mmWave. And we're streaming live on mmWave now. So this activity is occurring on mmWave, and you'll be able to see the level of activity as in the background while we're talking. And Phil's going to be helping us during the presentation with some live testing. But we first of all thought we'd just show you where we are, because you can probably see the Melbourne background behind us. But there's also some EME testing probes that you can see. But I wonder if you swap to the roving camera I've got and keep this microphone on, if you can just do that, and then I'll show you. I've got to turn the camera on, don't I? So now what we're doing is we're having a bit of a live look outside. For those that know Melbourne, we're just opposite Marvel Stadium. So we can see Marvel Stadium in the background. And if I scroll around here, this is Docklands Harbour. So we have a pretty good view from our lab environment. Now I mentioned two spectrum analyzers before. I'm going to show you those now, and we'll go in and do some live readings after. But I wonder what speeds you get on your internet connection. We just ran a speed test before, and we were getting 3.6 gigabits per second, or 3600, 36112. So that's live on millimetre wave, and that's about 10 times faster than the normal 5G. And what we've got here is a view of the millimetre wave spectrum. And as you can see, it's very efficient. There's not a lot of activity, even with this HD quality video. The base station that we're connected to, we'll show you in a slide in a minute, but it's directly across the road. And if you can see two green painted lines on a building, we're just above that base station. So I don't know if you can see that, but we will be doing live tests with Phil and Steve. This is a project in collaboration with our graduates, and we've got Zoe and we've got Lucinda here, and they're looking at the ACMA map of registered sites, and we're looking around Docklands at the moment. And I don't know if anyone is online from the ACMA, but there's a green dot in the middle of the water. Now, I don't know if you can see that, but according to that, that's the entry to Etihad Stadium. Now, I would suggest that's probably not the entry to Etihad Stadium.
Submarine entrance.
Maybe it's the submarine entrance, but if you go back to the other camera and we'll start our presentation. So I hope you could get a brief look at where we are, but we're going to share a quick presentation to give you some background on what we're doing, what the project's about, and then we're going to do the live testing with you. Now, by live testing, it is live testing. We're going to show you the screens, and just as a heads up, we want you to write down the numbers we measure, pop your results in the chat. So just as a heads up to get ready for you taking the readings. So we'll have all of the people online are able to do that. Now I'm going to share my screen. So you just saw this before. This was the picture on a really sunny day in Melbourne. Most days are like that in Melbourne. It's a little bit of cloud at the moment, but that's the view out of our window. It's basically a collaboration and learning project with our graduates. They're the future. All of our young professionals and all of our graduates are the future of telecommunications in this country and indeed the world. So we're partnering with them on a lot of our project. What are we actually doing? We're testing the 5G performance, we're testing the customer experience, and particularly the new products and the fixed wireless access products. What we're streaming today on is actually a fixed wireless access antenna. So it's mounted outside, providing us that high connectivity to the network. Inside the apartment, when we wrote this PowerPoint presentation last week, we had 75 devices. After the weekend, we've now got over 100 devices in the apartment. Now that's an insane number of devices, and we'll show you some of those, but we're doing a variety of use cases. Gaming with the graduates and the teenagers is a particularly popular one, as you'll see in a minute. And of course, with this number of devices, we need to test the EME levels. How safe is it to work and be in here? So this is where we are. We're at Docklands in Newquay Docklands. There's a red dot on the map that you can see. That's the building on the right-hand side. And if you look closely, we are where that yellow dot is. So we are in one of the upper floors of that building. Beautiful view, beautiful building. This is the view at night, and that's the Balti Bridge over to your right. So again, it's a hard task to do measurements here at night time. A bit about Telstra's 5G. We now reach over 75% of Australia's population, and that includes more than 3,000 suburbs. We're in over 200 cities and towns across Australia. And I guess our mission is to bring better connectivity to everyone, especially with 5G. And we're going to be rolling it out, to more areas across metro, regional, and particularly rural Australia. We're reusing some of the previous 3G frequencies to help us do that. What's our history with millimetre wave? Well, last year, in fact, we celebrated 5 years of 5G. Now, we launched in 2019, but we've been doing a lot of work with millimetre wave since 2016, in fact. We had our first test bed here in Australia in 2016. That was in Melbourne. That was the first trial of 5G, I think, one of the first trials globally. And if we zoom all the way ahead to 2022, we're now in a live 5G millimetre wave smart apartment. The main auctions were last year. Prior to that, we were using scientific licenses to enable us to trial 5G. Here's a case study for those that are based in Australia. If you're overseas, you've probably heard of the Melbourne Cricket Ground. It's where we have the Ashes and where we have the Boxing Day test. It seats 100,000 people. We've got millimetre wave through the MCG now, and we're getting speeds of between 2 to 3 gigabits per second. but it's part of a new upgrade activity so that we can do an enormous amount of multi-viewer streaming, or we can really make the interaction with the audience a lot more, I guess, interactive and a lot more personal. How does 5G actually work? Now, it is important to understand the very basics of this, because this is what the sort of measurements are involved that we're doing. So when we talk about doing EME measurements, we're doing measurements on what's called the radio access network. Now, these are the cell towers. You can see a 4G one in the foreground, 5G small cells. Over on the left-hand side, there's a 5G macro. Now, the macro cells have beam forming. So you can see a couple of towers there that have beams that go to different devices. That's really important in 5G because it means that you can get greater efficiency and only send signals to where they're needed. When you're not sending them everywhere else, the efficiency increases and the background emissions also decrease. Now, the core network has been completely redesigned for 5G. It's now running on centrally based servers, and we're moving to the cloud for our 5G core. What that enables us is to slice or to provide certain aspects, certain elements of the core for different services, like emergency services, for example, or industrial, rural, and, I guess, medical applications. So basically the towers connect the devices to the core network. The core network manages all the traffic and all the utilization, and it decides what connection is best for you. So that's, in a nutshell, that's how the network architecture is. But importantly, what we're going to show you now is the beam forming part. Now, this is the neat part for this apartment building. So on the left-hand side is a graphic that shows what 4G antennas used to do, or still do, I should say. They send a signal in all directions, regardless of who's connected. With 5G antennas, it depends on the connection. We're only sending a signal to the devices that need connection. So if you think about the apartment building we're in, on the right-hand side, we've gone to the base station across the road, and we've tilted the antenna serving this apartment building up so that it can then send beams to the top of the apartment building. So we have one directly servicing this building as a trial and a use case. That's why we're able to get those insane and really good speeds up here. It's one of the use cases that we're trialing. Now, people ask us about spectrum. It's a really important aspect of 5G because up until recently, we didn't have any high band or millimeter wave spectrum. And essentially we were using the lower bands. Below 1 gigahertz is low band, between 1 to 6 gigahertz is the mid band. And the high band really starts technically from 30 gigahertz. We're using 26, but they call that millimeter wave. Now, because there's a lot of bandwidth available, up to 1,000 megahertz in the millimeter wave band, that means that we can provide extreme data rates and really enhanced capacity. The mid band, which is what most people connect on 5G at the moment, gives us the coverage and it also gives us capacity. But in the rural areas and in outer regional areas, we're using the lower frequencies to get the range, but it still gives us good throughput. So we can connect all of our IoT devices, but it still can give us 5G. Now, in the apartment, what do we have? Excuse me. We've got over 100 connected devices. It's a mix of mobile, IoT, and smart devices. Our primary connection is through 5G, and we've got the Google Home system running on mid-band and all the high-intensity stuff running on millimeter wave. And we've got a lot of smartphones and, as I said, the Google Home products. You can see a list. I won't read through all the list of the devices there, but we'll show you some of those working in a couple of moments. But there's over 100 connected in this apartment. As an example, as we walk into the foyer, we've got a range of, and I don't know if you can spot them, but there's even one of the early 3G Apple iPhones. I don't know what model iPhone it is. It doesn't work anymore, but there's a BlackBerry there. There's the first 3G video phone in Australia. It's an LG flip phone. And then in the foreground, we've got a lot of devices all running over 5G millimeter wave streaming YouTube. As I said, we do get really fast speeds. This is just a screenshot of the speed test that we got on this device. I think it was back when we started the project, and you've just seen another one that we had live just before. But it's not all about speed. This is what we can get to this apartment, but we can share that around. So, you know, most of the applications can run on much lower speeds, but this is the potential of what you can get at the moment. And with the devices coming into the future, when we can combine the mid bands and the high bands, we're going to be able to exceed this. And I think recently we talked about getting speeds of above 5 gigabits per second. Gaming has been an awesome experience in here. Now, what better way to try it than with our teenagers from the staff? So we did this on the weekend. One of our staff members had their family in the apartment on the weekend. And I swear, I don't think these kids moved the whole weekend. When they plugged it in, and Charlie, one of the boys said to me, Mike, the ping is awesome. It's 0 to 1. You can't get any better than that. And you can see photos there. They stayed there the whole night. And I'm sure that was them the next morning. But gaming at night time has been very, very popular because all of their games worked a lot better and they were hooked. We also have a lot of fun. And I talked about the graduates before, learning, experimenting and streaming. There's a few photos there of our team. We did a live stream on Facebook, YouTube and LinkedIn last week talking about the stories and the power of storytelling. We've got our graduates here connecting and testing devices. We even live stream cooking 5G pasta the first week, and that's turned out to be a bit of a hit. We've done testing, as you can see, and we've even got a smart coffee machine. So I had an espresso on the balcony and I had to make it over the smart app. We're going to do some testing. So Phil, look, these are the standards that we test to. Do you want to just run through the standards that we've got here, Phil, and just explain what they are for people?
So the testing we do is actually Australia has its own standard, which is the AES 2772.2. So that's the measurement standard that's utilised here in Australia. That aligns really, really closely with the IEC international standard, which is the International Electrotechnical Commission 62232. So there's a fairly close alignment between those two, but when you're testing equipment, doing measurements, these standards are actually what used, and Australia obviously uses 2772.2, but there's a big alignment between the two. 3 or 4 people from Australia who actually sit on the 62232 committee. The exposure standard is the limits that we do the tests to, and then with all the different equipment. We're spending a bit of time on the testing equipment because no one's really spent a lot of time from a mobile communications point of view getting a testing equipment. So we're actually working our way, because it's a new technology and it's in the mmWave. We've been working the last 5 years on developing new and more up-to-date measurement techniques. And so there's a combination of, especially because of the higher frequencies, spectrum analyzers and horn antennas are coming into their own. So we're testing some equipment that actually doesn't even exist in the market yet. So we'll talk about that a bit later on as well.
Sure.
When we're doing the testing.
So you can see 2 probes there, and the white antenna. The white antenna that's on the pole is the fixed wireless access antenna. That's the one we're connecting over now. And you can actually see the base station in the bottom right-hand corner. So the probe in the middle, we've got a probe that's a NADA 3006 round probe. But what's brand new is the one on the right-hand side. Now that's the new mmWave probe from NADA. It's specifically designed to work with the existing kit. They don't have mmWave in Germany, so we're trialing the first units that have come off the production line. They're due to be released middle of the year, but we're putting it through its paces here. I've got to say they're working really well, and we're using these to do our testing along with some calibrated horn antennas with a Keysight spectrum analyzer and an Anritsu spectrum analyzer. We're comparing them all, but that's what the new probe looks like, and we'll do it live as we go outside. Now, I think we might go and do some testing and then come back to this one. Should we do that first, yeah, Steve? We might go and get Steve. So I'll stop sharing. So let's go to the spectrum analyzers, and I'll try and move this as slowly as I can. Now, as I mentioned before, we got an awesome ping on the phone, and that was the speed we were getting. I'm going to do some live readings on the screen here. Now, without me running a speed test, I'm going to try and hold this still, and I'll just get Steve to look at the main screen. Is that behind me? Is that still? Is that
Yeah, that's
You're
good.
able to read that?
Yeah. Just hold still.
All right, I'll just hold it as still as I can. So, Phil, can I just check that we're actually, don't run the speed test yet, are we actually measuring the average? Are we displaying the average?
Yeah, it's the average over the last 32 sweeps. So it's about.
So do you want to point to where that is? Okay, so in the right-hand corner, and I'm trying to speak up because the mic's behind me. In the right-hand corner is the average EME level as a percentage of the general public limits. Now, if we read out what that is, I think I can't read it because I'm
3.0000045.
So 0.00045%. Now, I'd like you guys to make sure, people online, if you can double check that that's what you're seeing. Now, that's the call with the live stream and all the camera activity that we've got at the moment. What I'm going to do is get Steve to run the speed test on this one. Yeah, that's it. Yep. So you're going to see the 800 megahertz kick into action when we run a speed test. And it should bring up some activity any minute now. So the average should also increase. Now, when that finishes downloading, just pause that. So we've just paused it, and I'll, at home, if I can get you to write down what that number is, and then that's a comparison between what the network's like under very high load compared to what it's like when we're doing a Zoom call. So the activity is, if you can write that down and then work out how many times below the public exposure limit that is, that's your first test for the day.
10,000.
What I'm going to show you is a comparison to mid-band. Now, if I hold this still, what we're seeing on the screen is the 3600 megahertz 5G signal. Now, you'll see two markers on the screen. I don't know if you can point to them, Phil. There's two markers. That's 80 megahertz that Telstra has in the 3600 meg band. Now, think of that as a two-lane highway. Then what we're going to do is we're going to move across on the same scale and run another speed test, Phil. And this is now the millimeter wave frequency. And this is like an 8-lane freeway. So this is the advantage that millimeter wave brings. You get a significantly increased amount of spectrum, and that can handle all the speed and all the capacity and devices that are going to connect into the future. So I'll just move back a bit. And I hope you could see that okay, because that sort of illustrates, and I'm going to turn the camera angle around. I hope you could see that okay, because that illustrates really what the advantage of millimeter wave is, that you get a lot more capacity. We can do a lot more, particularly in those use cases like the MCG and Marvel Stadium, and in populated areas like the CBDs and train stations. Now, we're going to show you what happens when you're in an apartment building like this, and it's a 6-star rated apartment. So it's the energy consumption is, or the energy rating is, it's got a very thick window film tint. I mean, it's metallic tint.
Yes,
Plus, it's also a very thick glass. You do get a lot of attenuation through the window. Now, we can show you that live. So I'm going to... All right, so the purpose of the test here is we're going to run a speed test. We're going to run a speed test inside of this location, still connected to millimeter wave. We have a receive antenna, and we've got a spectrum analyzer. So when we run it, we're going to do a speed test and have a look at the spectrum analyzer. This particular one, you'll have to come in quite close, Steve, because it does flash a bit. So first of all, I'll run it before I do, I'll do a speed test before we open the door. And we'll just see if we're getting connection. And we are. Now, you can just see a little bit of activity. Now, if you open the door, Bill, you can probably see the activity's jumped up significantly. And we'll do that again in a minute. So the speed test has just stopped. So if we close the door again, I'll have to reset it. Now this is 5 dB per division for those that are looking at the science behind this. So every little division is about 5 dB. I'm going to run another speed test. Go. And we'll now get Phil to open the door. Yep, we've got speed test, open the door. And there we go. We are getting between 20 to 25 dB of attenuation through the door. Now, that presents a challenge to us in a number of ways. The main challenge for us is, so when we have devices in here, how do we get the millimetre wave signal inside the apartment like this? That's one of the reasons you have an outdoor antenna and you provide Wi-Fi connection inside. But of course, if you have a millimetre wave device, then if you're near the window, it'll work. Chances are, if you're in the middle of the apartment, it will fall back to the mid-band or other frequencies. So part of our work here is characterising the attenuation inside the apartment like this. One of the devices we do have, I don't know if you can pan around to the floor, but hey Google, start the vacuum.
All right, starting Dbot vacuum.
So we have a device here that will, it's very good after a long weekend with teenagers. It should start, there are. It's going to go off and vacuum the apartment now while we're working. So that's just one of the devices that we've got running over the network. We can probably send it back in a minute. So the vacuum's going to chase me. Hey Google, send the vacuum home. Now I mentioned before about a number of devices. These are all, now I'll hold this quite still, I hope you can see this. These are all streaming 4K video and you can see the quality of some of those video clips there. And I think I showed you those early on in the picture. But this is the live version of those videos and those devices all over millimetre wave on our network. And if we go out here now, Phil, you were going to run some live tests on mid-band and do some readings inside and outside. Is that right, Phil? Or Steve?
Yeah, I'm just setting up for.
Phil's just setting it up. But we'll go outside while Phil's doing that, and I'll just show you the probes. So this is the new NADA millimetre wave probe. It's got a horn antenna in it, and you have to point it towards the source. In our case, it's the base station. And it's a really good probe for, it's got a down converter in the handle. That's how it can work back on the existing SRM. And this is the mid-band probe that we're using. And as I mentioned before, we're measuring the levels outside on the balcony using this equipment, but we've also characterised what the levels are like inside through the whole apartment. And we're going to show you the results of that afterwards. If I slowly turn around, awesome view in the reflection, but that's where we were before doing the, we were doing the attenuation test through that glass door. Okay, Phil.
Yeah, so we're ready to do the outside.
All right, we're going to do a reading outside and I'll get you to explain what we're doing and I'll move it on the spectrum analyzer.
Right, so what we're doing is we're measuring it's a 32 sweep average just for simplicity and comparison to the previous measurements, but we're actually measuring the entire spectrum from 420 megahertz all the way up to 6 gig. And you can see 420 up to 6 gig. And what we're doing is if we hit evaluation and integration, we can actually see what the average is. So the average is about 0.08586% of the general public exposure limit. So that's what we're seeing on the balcony, based on all the different sources, and you can see all the different types of sources there in the environment. This is actually 5G gigahertz Wi-Fi. This is the 3500. That'll be 2600. Wi-Fi's in there, 2100, 18, and then there's 900, 850 and 700 bands. And there's some little two-way radio stuff that we can see. So we're getting about 0.082% as an average over those 32 sweeps.
So is that live on the Melbourne networks now? So
yeah, that's what we're
seeing on the balcony.
Yeah, that's what we're seeing on the balcony. And then what we can do is we can move the probe inside.
So that's with the probe. So while you're resetting that, I'm just going to go over and see if we found out how many sites there are in Melbourne. Did we end up finding out how many sites there were in the Melbourne CBD?
Over 2,000.
Over 2,000 on the ACMA database. So when we look outside, we can actually see most of Melbourne, and there are over two. So what are you looking at there? Path attenuation, is it?
This is the elevation profile to where we are from this side.
Oh, beautiful. Fantastic. So with over 2,000 sites in Melbourne, what we were measuring before was the background level of all the active sites at the moment. We've come inside. So Dr. Phil, what are we seeing now?
So we're seeing about 0.036, 0.037%. So we've seen about a 50% reduction. I think from memory, was it about 0.08 from memory? The really interesting one is you can see these frequencies here that we didn't see before are actually the Wi-Fi in the apartment. And we can also see that the 2.4 gigahertz Wi-Fi has extended quite significantly. In fact, the greatest sources in the apartment are actually not the mobile carriers from outside or the UHF radios, but actually the Wi-Fi that's actually in the apartment.
So what would a typical Wi-Fi level be on this screen?
That's a difficult one. I have to do some adjustment. So frequency max, frequency min.
So this is the 5 gigahertz Wi-Fi, is it?
Yeah, this is the 2.5 gigahertz Wi-Fi frequencies. So on average, I'm just going to let it run for a little bit to see if it stabilizes. About 0.016% 5G, 5 gigahertz Wi-Fi in the apartment. And that's not just, I would say that's predominantly this apartment and its devices, but there are other devices in the apartment complex that will contribute to that. And if you want to have a look and see what the 2.4 is doing.
So for those that have a lot of Wi-Fi at their place, we've got many devices connected on Wi-Fi running at the moment. This is probably a really good little test for you.
There. Just bring this back up. And that's the 2.4 gigahertz Wi-Fi, which is about 0.026, which is contributing to that total number. So you can see the 5 gigahertz and the 2.4 gigahertz. It's still really low, but they're the main contributors to what's actually.
All right. So I know it's in the afternoon. We're going to pause for some questions in a moment, but I often get asked what's my favourite device. Well, I do love the smart coffee machine. There's cookies on the table, but I must admit that, you know, it's the afternoon. I feel like a cup of tea. So, hey, Google, boil the kettle.
Sure, turning on the smart kettle.
So it's going to boil the kettle. I'm going to make a cup of tea. We're going to come back and have some questions. And then that looks like you've got the site map there on your laptop. And that's, if I scroll right in, are they all sites in Melbourne?
Yeah, it's like showing like around 4,000 sites there.
4,000 sites in Melbourne. That's quite significant. And we were measuring the total levels. So what are your favourite, I'm putting on the spot, girls. What are your favourite devices?
Coffee. So
Coffee machine?
Yeah.
Yeah.
I really like the vacuum.
You want the vacuum?
Yeah, vacuum's pretty cool.
All right, let's go. We're going to go back for some questions. We've got to show you the PowerPoint, but we might switch this camera off. Just to finish off, and then it would be great if we have some questions. We've done a lot of testing over the past few weeks, but to give you an idea of what we've found on mmWave, the balcony is definitely the highest, and you saw the inside attenuation of 20 to 25 dB. But when we ran fairly high intensity devices like you saw with speed test, of course, you've got to measure the average level. So these results are average levels. The highest we measured was about 0.004 just over 0.004%. And inside, near the window and the lounge and kitchen were, well below that. We're talking 100 times below that. So really, when you consider it, millimeter wave, and you saw the efficiency of what we're doing there, and there's a photo there of the base station highlighted in yellow and the probes that we were using. So very, very low EMF levels inside and on the balcony. What's our sort of initial conclusions? Because we're still gathering a lot of data. So look, our initial conclusions, millimeter wave 5G is extremely efficient. You probably saw the activity running when we were, talking before, and it was HD video. We have a number of things streaming. The levels are really, really low. And as the range of levels we're getting at 0.0042 to 0.400, I need my glasses on. And, in normal everyday activity, most people aren't running speed test every day. The background levels, like you saw, are very, very low. And, to put it in perspective, well below 1% of the public safety limit. So look, I hope that gives you some sort of indication of, what we do in why we're doing this testing. It's to really build on the knowledge we have. We want to share it globally. That's one of the reasons we're presenting, and it's a really good moment for us to present to the ARPS group today. And we look forward to taking some questions. So I think the questions are going to come in by chat, and I'll just wait for Drew, I think it is, that might pose some of those questions. But in the meantime, I wonder who did the calculations before. So we looked at what the average levels were, and I didn't write them down. Did you write them down? I hope somebody wrote them down. I think they were I actually didn't write them down. So that's a tick or a cross for me.
The test was 0.0. We'll go with 0.01.
I think it was about
That's the millimeter wave.
Yeah, so I might defer to someone that actually wrote them down.
It was actually 0.0076.
0.0076. And we'll have a look in the chat to see who got the calculations right in terms of how many times below the RPSS, the general public limits. I know from my slide, because I checked it earlier, we're well over 10,000 times below the public safety limits, and that was outside on the balcony. So now I think I can't hear anyone. I don't know if anyone's got any questions.
So we've got two questions through the chat, but firstly, I wrote down that you'd said it was 0.007%. Which is something like 13,569 times below. But yeah, I haven't seen others post those numbers into the chat. But yes, that agrees with what you just said. There's a couple of questions coming in now. So the first one is a bit of a two-part one from Victor Leach. It says, this is pulse modulated radiation. Are the frame breaks still at 217 hertz?
No, that was what was used in the GSM days. But this is, well, this is actually, this uses a different modulation scheme, similar to 4G, but it's not 217 hertz. No, it's much faster than that.
Okay. The second question, or the second part of the question is, so the antenna on the street poles will connect to the antenna on your house, and you would need an antenna in the house as well?
Yes, that's right. So what we have, it depends. There's two ways of doing it. Do you want to grab the device off the wall, Steve? The 5G device off the window. So the outside antenna that we had here, and if I swing my monitor around, no, you can't quite. So you can just see the base of it over here. I'll swing this back. That has an Ethernet cable, so the modem is already built into that antenna, and that provides you with a Cat6 cable into a router. So that you can then connect it to a Wi-Fi router, you can connect it to Ethernet through your house. So that's one option. And that obviously provides you with very, very good connection and a very stable connection. This device here, which is a router that sticks on your window, so the back of it actually goes onto the window like that. It connects to millimeter wave through the back and provides Wi-Fi through the front. So that's a radio connection or a Wi-Fi connection.
It's not transmitting.
It's not transmitting 5G. It's transmitting Wi-Fi inside and 5G outside. So that's another option. And you can get, do you want to get me the MU500? It's just on the display there. So these are for fixed wireless access. You fix this on the window, and it connects up to the base station. The ones that we find very, very useful, and it should just be sitting, sorry. The ones we find very, very useful are these little devices. This is a Telstra 5G Wi-Fi Pro, and basically it's millimeter wave. You can connect it up via USB-C or Wi-Fi, and it will plug into your laptop. We get connections over on the window there of around 1.5 to 2.5 gigabits per second because we're going through the window. So there's different ways you can connect up.
This is no different to a mobile data 4G.
Yeah, this is like a mobile data device, but it has millimeter wave as well. So
thank you.
Hope that answers
There's another question's come in from Martin Gladhill. Is there any idea why the intensity of the millimeter wave varies so much across the bandwidth of the signal?
So that's, you mean across the 800 megahertz, I think is what Martin might mean. It does vary, and what the network does is it chooses the best, there's 8 100 megahertz channels stitched together. So to get 800 megahertz, they've got 8 individual 100 megahertz channels, and it's looking at the radio profile and the amount of data we need, and then it picks the best number of channels to use for the application we have. So when we're not using very much, it's reserving some for others, and it's allocating some data. They're called radio resource blocks, and it's allocating some for us. When we want a lot of data like we did in speed test, you can then see it starts to activate the other channels. Now, the key thing about data utilization when people use devices, the network will look at where you are, what you need to do, and what the quality of your connection is, and then it will choose the frequency that gives you the best connection. If it's a high intensity connection like we just had, it says, right, you need millimeter wave, I'll allocate you this. If it's a IoT device that just says, I just need to know whether it's on or off, it might choose another band and send that signal depending on the distance. So Martin, it's really about the utilization and it choosing the best path for your application. If we're in a different floor, we might have been using different parts of that band.
Thank you. And Ray McKenzie did comment that the speed test was about 0.001% for all devices and about 0.0005% for about half.
Fantastic.
There was a follow-up. Sorry, there was a follow-up question as well from Victor Leach just saying, can you let us know what the frame breaks are?
The frame rate. Okay, well, it depends, I guess, on what you're doing, but it's a 10 millisecond. It depends because the way that 5G works is that you've got a 100 megahertz carrier, and then you've got secondary synchronization blocks. So your synchronization signals occur roughly in the middle of the carrier, and they occur on every 10 milliseconds, I think, 10 to 20 milliseconds. So there's a frame rate of 20 milliseconds for your secondary synchronization block. Then, of course, you've got the data that sits on top of that. So there's a number of, I guess, housekeeping synchronization signals that occur depending on where you are. So that's... and then the TDD as well. Oh, well, yes, sorry, I should have said the whole thing before is we're using the same frequency for uplink and downlink, so it's time domain duplex. So at the moment, it's set to a 3:1 ratio. So you allocate it, it's 3/4 of the time it's downlink and 1/4 of the time it's uplink. So Victor might have been asking that question. So yeah, there is a ratio between your uplink and your downlink. So it's never transmitting at absolutely 100%. It can't do that because it allocates part of the time for uplink. So will talk be incorporated in the millimeter waves, or will it use a lower frequency like 1800 megahertz for the stability of talk? Sorry, I didn't talk? So you mean the voice? Yeah, so voice, I believe, is what's in that question. Oh, okay. Okay, so it's no. So voice is converted to data, so it's all data. But it will, like I said, it will choose the best frequency, and often it'll prioritize. If you need a voice call, it'll prioritize voice in the network to make sure that your call is stable and uninterrupted. Because data, like when you're watching a YouTube clip, it'll buffer, like it'll send you a lot of data and it'll build the data up or the video up in the buffer. And data works the same way. If you're downloading a file, when we do the stream like this, obviously it's processing it very quick. but voice will always be a priority because that's typically the way networks are set up. It will choose the frequency of best connection.
Excellent. Look, that is all the questions that we have. I really appreciate your time today, guys. It's been a great presentation. Good to see the interactiveness of walking around and seeing it all in action. I guess.
I wonder what would be your best, what would be the #1 device for you? What would you like if you could come and have any device here?
Ooh.
Would it be the smart coffee machine? Would it be the...
Smart coffee machine would be my preference. Yes.
You want the...
I want the speed.
Phil wants the speed. Yeah.
And the network to go with it.
Yeah, there's a few people asking for coffee. I can tell you what, that's exactly what I'm going to make in a minute. Once this is done, I'm going to make a really great coffee, and we're probably going to bake some hot cross buns. So we've done our live measurements. There's over 4,000 sites in Melbourne, including one in the middle of the harbour. That's the entrance to Marvel Stadium. So someone will have to correct that. I'm certainly not taking that submarine entrance, but you know, if we can summarise it, we're live on 5G now. The levels are extremely low, even with all of the activity running in the middle of the day in Melbourne. The measurements fielded from outside to inside demonstrate there is a reduction. The Wi-Fi comes up inside, which you'd expect, but the levels were still extremely low. So, you know, we'll be sharing all of this data and obviously presenting it later in the year when we've written it all up, because we're continuously recording it. But to actually live stream it and show it to you, it's been our pleasure.